In this video, we're going to talk about 9.5 alternating series. Our objectives will be to use the alternating series test to determine whether an infinite series converges, and then to classify a convergent series as absolutely convergent or conditionally convergent. So let's go ahead and get started. The alternating series test tells us first, we need to know what an alternating series is before we talk about the alternating series test. So an alternating series is a series whose terms alternate in sign. For example, the series from n equals 0 to infinity of negative 1/2 to the n. Not sure you can see that, but there's a negative right there in front of the 1/2. Make sure that that stands out to you. So that's the same thing as series of n equals 1 to the infinity of negative 1 to the n times 1 over 2 to the n. That's an alternating series. Could also write that as n equals 0 to infinity of negative 1 to the n over 2 to the n. So more specifically, this is an alternating geometric series with r equal to negative 1/2. And we know that that's going to converge by the alternating series test. I'm sorry, converges by the geometric series test. Because absolute value of r is less than 1. So if we wanted to know what that converged to, just as a refresher, s equals a naught is going to be 1 over 1 minus r is 1/2. 1 over, and it's a minus a negative 1/2, so that's plus 1/2. So that's 1 over 3/2 is 2/3, just as a reminder of what's going on there. Now for the alternating series test, let an be greater than 0. The alternating series of n equals, and it can start at 0 or 1 or whatever, there of negative 1 to the n an, where this is the sign changer. We're going to kind of ignore that part and focus in on this part that's not the sign changer. Again, this right here is the sign changer. We're going to focus in on that part. So it's going to be in one of those two forms right there. That converges under the two conditions that are met. If the limit of n goes to infinity of an equals 0. So it passes the nth term test, and it is decreasing like that. We're not worried about the part about continuity here, but it is going to be positive right there. And it's going to pass the nth term test, and it's going to be decreasing. Note that number 2 can be modified to require that the n plus 1th term is positive and less than or equal to the previous term for all n greater than or equal to some integer capital N. Like we've seen before, it just needs to meet these conditions after some point in the series for it to be convergent. The majority of these tests are applicable as long as the conditions hold for some index n greater than or equal to capital N. So let's go ahead and let's look at this with the harmonic series here. N equals 1 to infinity of negative 1 to the n plus 1 of 1 over n. It's going to be 1 over 1 minus 1 over 2 plus 1 over 3 minus 1 over 4, so on. So we know the harmonic series diverged, but we're interested here if this converges on the condition that it is an alternating series. Does it meet those two requirements? So condition 1, limit as n goes to infinity of 1 over n equals 0. Check. It passes that test. Okay? I'm only interested in this non-alternating part. Condition 2 is 1 over n plus 1 less than or equal to 1 over n for all n greater than or equal to 1. Let's see. So cross multiply here, since n's are positive, is n less than or equal to n plus 1? Yes. 0 is less than or equal to 1 for all n. So that's true. So therefore, an plus 1 is less than or equal to an for all n. Greater than or equal to 1. So the conditions for therefore the series is conditionally convergent by the alternating series test. From this point forward, I'm just going to say AST for alternating series test. Okay. It's important that you say it's conditionally convergent. We're going to talk about another type of convergence here in just a little bit. So does the series -8 to the n over n factorial converge or diverge? So we need to look at that as n equals 0 to infinity, -1 to the n, 8 to the n over n factorial. So our an here is 8 to the n over n factorial. And let's look at what an does graphically. So it's going to, actually, let me just graph this in Desmos so you can see. Eight to the x divided by x factorial, and see that it goes up and up and up and up. Somewhere here reaches a maximum, and then it's going to start coming back down, never to go up again. Now I'm going to prove that to you with a derivative because the graph is not proof, because you don't know if it's going to go up or down again in a second. But let's go ahead and look here, and it appears from the graph that it goes up, reaches some maximum, and comes back down, and that this maximum is at 7.49 something 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 something. and some huge number here, 422.6 something, something, something. So that means that for all n greater than or equal to 8, I'm going to let capital N be 8. I think that I'm going to be able to meet the conditions of this test, that it's going to go to 0 down here. And I think that I'm going to be able to show that it's decreasing just looking at the graph. So let me try that. So let's start with condition 1 to show that the nth term goes to 0. All right, so just using the general knowledge that we have from how quickly these functions grow, we said that the factorial function is the fastest growing function that we know about and grows faster than any exponential function. And if the faster growing function is on the bottom, we know that this is going to go to 0. So check. Eventually, it's going to get there. And we see that on the graph. Just don't know, does it go up and down a little bit before it gets there? So condition 2, we want to show that an plus 1 is less than or equal to an, at least eventually. For some n greater than or equal to capital N, right? For all n greater than or equal to capital N. And we think from the graph, capital N is equal to 8. So an plus 1 is going to be equal to 8 to the n plus 1 over n plus 1 factorial. And an is going to be equal to 8 to the n over n plus 1 factorial. Now we want to show again, we want to show this an plus 1 less than or equal to an. So let's try that. 8 to the n plus 1 over n plus 1 factorial less than or equal to 8 to the n over, this is n factorial, n factorial. So we're going to turn this into 8 times 8 to the n over n plus 1 times n factorial less than or equal to 1 times 8 to the n over n factorial. And because all of these things are positive here, then that means that if I divide through here, my statement is 8 over n plus 1 needs to be less than or equal to 1. So 8 needs to be less than or equal to n plus 1, and n needs to be greater than or equal to 7. Great. 8 over n plus 1 times n times a sub n. Less than or equal to a sub n. So 8 over 1 is less than or equal to 1. Right. So, and we looked at the graph here, 8 to the n over n factorial, and 7 was good, but we're actually going to choose a number bigger than that. We're going to make sure that we choose at least 8, so that we get on the other side of this maximum here. So I like to actually do derivatives and get this minimum or maximum point up here. I just don't know that you know what the derivative of n factorial is right now. So that's why I chose not to use that method. But we can conclude here that for n equals 0 to infinity of negative 8 to the n over n factorial is conditionally convergent by the alternating series test. All right. Because it meets the conditions, but it would not have been, we don't think that it is necessarily convergent on its own without the fact that it is alternating. We just know that it's convergent. Let me just say that. Let's not talk about conditional or absolute yet. Convergent. So now we're ready to talk about the difference between absolute and conditional convergence. And we're going to want to identify when it's conditionally convergent, when it's absolutely convergent when we use this test. So notice that the alternating harmonic series that we discussed in the first example provides an interesting example because it actually is the alternation which allows the series to converge. The fact that it's an alternating series is the condition which allows it to converge. So recall that 1 over n by itself diverges. This leads us to our next theorem. So without the sign changer here, with the sign changer here. So absolute convergence tells us if the series, the absolute value of a sub n, so ignoring the sign changer, converges all by itself, then the series converges. Absolute and conditional convergence definitions: the series is absolutely convergent when the absolute value, without the sign changer again, converges, and it's conditionally convergent when the series converges with the sign changer but its absolute value diverges. It converges on the condition that it is alternating and passes the alternating series test. So it is conditionally convergent. Okay, because it's convergent on the condition here that it was alternating. That's the only reason why it converged. It didn't converge otherwise. If the absolute value of it converges, ignoring the sign changer, it's absolutely convergent. So let's go ahead and look here at this next example. Consider the series of summation from n equals 0 to infinity of -1 to n, n factorial over 2 to the n. Determine if the series converges or diverges, or if it converges, does it converge absolutely? The first thing that I want to do before I do anything else is look at the limit as n goes to infinity of n factorial over 2 to the n, because if it doesn't pass this, it doesn't pass the nth term test, and it fails no matter what. So looking at this piece right here that's an, let's look at the nth term test. N factorial grows faster than 2 to the n, so this is going to go to infinity. So it fails the nth term test and diverges by the alternating series test. We may not have said that before, but if it fails any of the conditions of the alternating series test and it's alternating, then it diverges. There's no ambiguity in the alternating series test. That's one of the reasons we like this test. So let's look at another example here of -1 to the n over square root of n and determine if this converges or diverges. So we're going to look at an equals 1 over n to the 1/2. That's a divergent p-series. So it's not absolutely convergent. So let's go ahead and check the alternating series test here. Limit as n goes to infinity of 1 over n to the 1/2 is equal to 0. Check. And I want to see if f of n is equal to n to the -1/2. F prime of n, since this is easy enough to differentiate, is -1/2 n to the -3/2, like that, which is equal to a -1 over 2n to the 3/2. Remember that n is greater than or equal to 1 here. So this is going to be, let's look at my first derivative test just to prove this, that here's 0 right here is the only interesting place where this has a vertical asymptote. Over here, this is always going to have to be positive because there's a square root here, and that's always going to be positive no matter what. But actually, just the function does not exist over here. And then over here, this is going to be negative. Once I stick in a positive value, take the cube root of it, or take the square root of it, cube it, That's going to be positive in the denominator and negative in the numerator. So this is decreasing always from 0 to infinity. So it's definitely going to be decreasing from 1 to infinity there. So that's good. Let's do it the other way. Let's see if I can prove that 1 over the square root of n plus 1 is going to be less than or equal to 1 over the square root of n. And I want the square root of n needs to be less than or equal to the square root of n plus 1. And we can square both sides since it's positive and not lose our direction of our inequality sign here. N less than or equal to n plus 1, 0 less than or equal to 1. All of that is true. So condition 2 is met. For all n greater than or equal to 1. And so it is conditionally convergent by the alternating series test. All right, let's go ahead and look at the next one. So consider the series summation n equals 1 to infinity, -1 to the n times n plus 1 over 2 over 3 to the n. Determine if the series converges or diverges. If it converges, does it converge absolutely? So is this an alternating series? If not, the alternating series test doesn't apply. Write a few partial sums. Let's see what is going on here. So this is -1 to the n times n plus 1 over 2 is the sum of the first n integers. So this is -1 to the first here over 3 to the first. And then this is plus, and then -1 to the third over 1 plus 2 is going to be 3 over 3 to the second plus add 3 here, -1 to the sixth over 3 to the third plus -1 to the 10th over 3 to the fourth. And so on. So this is not an alternating, series because we don't see it going plus minus plus minus. This is going minus minus plus plus right now. So this is not an alternating series, but let's see if we can test for absolute convergence anyways, because we might be able to test to see if the absolute value of this thing converges. But let's test for absolute convergence. because whether this is positive or negative, if there's this sign changing going on at all, it's still going to converge if the absolute value converges. So let's let an equal to, forget about that -1 to the n part, is 1/3 to the n. So we're looking at 1/3 raised to the n. This is a summation from n equals 1 to infinity of 1/3 to the n. Watch out, this is starting at 1, not at 0. So this is actually 1/3 times plus, and then 1/3 of 1/3 is 1/9 plus a 27th plus so on. So this is my A0 is equal to 1/3, and my R is equal to 1/3. So this converges absolutely by the geometric series test. And I can actually tell you that S is going to be equal to 1/3 over 1 minus 1/3. It's going to be 1/3 over 2/3 is 1/2. All right. So the alternating series test, apply the alternating series test only to alternating series. If you're not sure, check to make sure that it's alternating series. Some alternating series do converge under certain conditions. Check these conditions too. Some alternating series converge when their positive counterparts do not. This is the idea behind conditional convergence. So that's basically it for this video. I'll say check for absolute convergence first, using the other tests that you know up to this point. Anytime that you have a test where you are taking the absolute value, you're figuring out absolute convergence, and you are going to need to say so if it had a sign changer in it. So that's going to apply not only to the alternating series test, but we have the ratio and root test coming up. I think they're coming up next. And they have absolute value signs in their tests. So those also are testing for absolute convergence. Make sure if you don't have a series that only has positive terms in it, that has some positive, some negative, and you use a test that has an absolute value in it to change all those terms to be positive, that you state that the series converges absolutely. That's something that you should be doing whenever you're using absolute value bars to determine convergence. If it was already positive and you tested it without taking the absolute value, that wasn't the reason, then you can just say that it converges like we did before. If it converges conditionally because it was an alternating series that had the nth term go to 0 and was decreasing, less a sub n plus 1 was less than or equal to a sub n for all n greater than or equal to some capital N, then you can tell that it's conditionally convergent. It's convergent on the condition or because the conditions for the alternating series test were met. I hope that makes sense to you. We'll come back and we'll talk about the ratio and root tests next time. Probably some of the most important tests that we're going to use. We're going to use them when we see factorials. We're going to use them when we see nth powers. For the ratio test, for the root test, we use it when we see an n to the nth power in the problem, or we see a lot of things to the nth power, everything raised to the nth power. We'll be able to use that. All right, that's it. See you for the next video.